First thing first, good afternoon, everyone. From Michele Marelli. I'm part of Particle Works Europe team, and I'm happy to see all of you here interested in how virtual prototypes with particle works are validated, increasingly validated on different topics. And I'm excited because today we have a very interesting agenda with a lot of applications. So yeah, let's just jump into it. So the agenda is divided and shown in this slide. We can see that we will first introduce the methodology, Particle Works, for those of you that are not familiar on it. And then we will understand why we see Particle Works applied more and more in engineering. There are clear trends that push towards the digitalization of prototypes. And then we have several validations from our partners in the fields of transmission, e-motors, piston and engine cooling, weighting, so external car weighting, and plastic recycling. So we will see different type of validation, flow validation, as well as temperature prediction, and we will detail all of them. So you see here the companies that presented in several public conferences about these results, and we will, of course, reference those papers later on. So let me just introduce the method first. So Particle Works is a fluid dynamics tool, software, CFD software, that is a little bit different from conventional mesh-based CFD because it doesn't require this step here that usually takes quite long preparation. So whenever I use mesh-based CFD, I have to prepare my geometry from the CAD, simplifying it, and also perform a mesh. So create a computational mesh that is the basic of our simulation. With Particle Works, we can just jump start and go to the CFD setup and the simulation. So here we have a visualization of the differences. On the left, we have the computational nodes pre-calculated during conventional methods. In Particle Works, on the other hand, we have particles that are themselves the simulation nodes, and they are automatically computed at the beginning of the simulation. Okay, so we don't have to deal about this step, and they are automatically generated. Of course, this approach is very suitable whenever we have a splashing phenomena, like in gearbox lubrication or multi-phase phenomena as well. And in general, the workflow here, we are looking into 1 day simulation workflow for cases that previously required more than weeks, okay? So we will see the applications. And if you start to understand, if you start to try to use mesh-based CFD to the application that we will see, really, that will require a lot of more effort, both on the hardware side and also on the pre-processing side, so man-hour. So in general, what we are looking at, it's a simulation, fluid simulation tool that doesn't require the mesh generation, so you can directly use the CAD as it's designed by your design department. It's very simple to set up a numerical setup and a numerical simulation. And also, because the algorithm behind the Particle Works are easily parallelizable, we can take advantage of GPUs, of graphic cards. And because of that, we can have more compact solution in terms of hardware. We don't need a cluster with thousands of cores, but we can really leverage the, let's say, computing revolution that we are seeing in graphic cards. So let's talk about trends. Why now? Why simulation is more and more applied in engineering? Well, there are several reasons. Of course, we are seeing a world that is increasingly digital because of different trends. Of course, COVID and supply chain shocks pushed and made this transition towards digital faster in the last years. So in general, by digitalizing the prototyping phase, you can have a faster R&D, you can avoid supply chain shocks, so you're not stuck because of price inflation or materials availability. And moreover, the digitalization of the R&D and engineering can actually improve, as it's shown by this McKinsey analysis, improve the value of your product because you reduce time to market, you increase the performances of your system. So by using digital prototypes. And also, as mentioned, we are running on graphic cards, and the value you get of computing power per dollar, it's every day higher. We all know the performances of NVIDIA, of course, pushed by AI related tools, but particle works and simulation, moving particle simulation can benefit in the same way. So we are seeing that every 1 or 2 years, simulation times decrease by a factor of 1 or 2. And the solution here is not just about fluids, it's about also other aspects that your system might have, like airflow, powders, or let's say temperature evolution of your system. So inside Particle Works, we see different modules in the same license, in the same graphic user interface. So you can integrate different aspects of your model, and I will try to give you visibility in that regard with the examples. So most of the validation we will see today are from our conference. It was held in June last year, and I will include also at the end of the presentation the official invite to the next conference that is going to be in September in Frankfurt. So the results, as mentioned, are coming from our partner that decided to present publicly. So let's see the validation, and let's start with transmissions. One of the first example of applying this approach was applied in 2019 by Comer Industries. They develop transmission for different type of heavy-duty, let's say, vehicles. And we see here a comparison between the standard approach, the testing approach with clear casing, and the lubrication prediction by the software. It's very interesting because you can see clearly that the film of oil formation, it's matched quite accurately by the simulation. Of course, the simulation allows you to extract more value because you can inspect regions in a quantitative way that with the experimental setup you can only guess. So to validate that, we compare different running and let's say rotational speed and directions, and we evaluated together with Elisabetta Fava the amount of oil in different regions. So as you can see here, the engineer in Comer Industries, let's say, correlated different areas, and 4 means a good lubrication level. And we can see clearly that for this condition, there is good lubrication, while on top, there are bearings that are not lubricated, and it's confirmed by the simulation. So not only fluid-related topics can be applied also to gearboxes, because right now we have a thermal solver in Particle Works. So basically the idea is that you can not only predict heat transfer coefficient due to oil, but you can also let's say, solve for the temperature prediction in the solids. In this example, we have first a CFD only simulation in particle works for oil that cools the coils of DC motor in this case. And then we can transfer to the, let's say, thermal solver integrated in particle works for the prediction of temperatures, okay? So let's see this method applied in the gearbox example. We can see here actually on the fluid side the temperature evolution of the fluid as well. So effectively you can analyze flow distribution but temperature distribution as well in the fluid and in the solid. You can see here that because of the bearings heating, there is some build-up of temperature close to the bearings. And on the right, we are simulating also a an external cooling system at the bottom, some water flowing and cooling the bottom of the gearbox. And we can clearly see that the average temperature of oil is lower because of that. So this is the most complete example of temperature in the solid that transmits to the fluid, also the fluid temperature that transmits to the fluid, and you can transiently see what is going on in your system. Let's see a similar example of temperature prediction. In this case, Carraro applied this method both, again, to evaluate the lubrication, but also understand the temperature behavior of the system. The objective was, let's say, there were several objectives here. First, of course, predict oil flow, and then compare the solver, the thermal solver inside particle works with ANSYS mechanical results. And at the end, there were also thermocouples placed at the bearing side to understand what was the temperature in that area with respect to the simulation results. This is the transfer box they analyzed. And here are the initial results from CFD. So particle works prediction of flow for 4 different conditions, clockwise, counterclockwise rotations. And at the end, you can see that the output is actually the heat transfer coefficient due to oil splashed on the gearboxes, okay? So we see here that, of course, depending on the rotational speed or the distribution, we have different amount of oil in different areas. Those maps were applied to the thermal solver to extract the temperature. What we are seeing here are temperature prediction, not HTC maps anymore. So basically, we applied those HTC to a thermal model in which localized heat sources were applied, because of course at the bearing side we have localized heat sources, and those heat sources are in, and we can clearly see that the higher we go in the gearbox, the lower the amount of oil and the higher the temperature. In order to validate that temperature distribution, as mentioned, there were several thermocouples experimentally measured by apps between the predicted and the measured temperature. We are looking into a gap below 10% that was the desired range by the customer. Let's move on now to e-motors validations. So this method, particle works, is applied also for e-motor cooling. So the idea is to use oil jets directly going to the most critical areas of the e-motor, like the windings here. We can see some in green, some oil accumulating around the windings. And you can see here jets actually coming from the center, rotating shaft. So Nidec PSA started to use the software a couple years back, and they were looking at this system. So they have a distributing cooling system that is partially rotating. And they first wanted to understand what was the flow split between the two branches of the cooling system, so the rotor and the gravity cooling, when the rotating velocity vary. Okay, of course, the higher the rotational speed here, the higher will be the flow going to the rotor. So to validate that, there were several conditions tested experimentally. So basically they increase the flow rate and increase also the rotational speed. Sorry, this is the flow rate going to the rotor, and the rotational speed of the rotor is on this axis. So as you can see, the measured in orange flow rate is increasingly important, and the simulation results match this trend, so are able to capture this trend with a gap of approximately 3 to 4%. So that was one important validation of the multi-phase flow and the flow split between different areas. But of course, this method is applied at the end to estimate temperature distribution, because temperature distribution and hotspots in e-motors are very important to understand if the magnets, for instance, are stable, are operating a stable temperature, because there are some materials in e-motor that are very temperature sensitive. So small variation of temperature could decrease the e-motor lifetime by a factor of years. So the full workflow implemented by Ricardo in this case showed not only the flow rate distribution in the distributing channels, but also air simulation to understand windage effects, and also the air gap windage effects, so between the rotor and the stator. And at the end, the simulation of oil jets. In this small example, we see oil accumulation in blue inside the e-motor and heat transfer coefficient estimation. So once you do the CFD, you can extrapolate the transfer coefficient and perform the thermal analysis. This was done. So what we see here is the output from ParticleWorks is an HTC map. And this map was validated with a thermal solver. So the temperature prediction here is from a thermal model integrating this map together with the losses, electromagnetic losses, estimated by other software like ANSYS Maxwell. And it's clear here that we have a hotspot, not that if you don't analyze the 3D structure of the model, you lose. On top, you see an hotspot here on the stator that is not well cooled. And to understand, again, the validation of this temperature distribution in the windings, Ricardo placed 6 thermocouples to the windings, to the coils. And we can see here the differences between the temperature prediction in ParticleWorks and experimental. We have a gap below 3 degrees Celsius, and the max target, so the target from Ricardo was to have a gap below 5 degrees. So well in the range. And we can see that, yeah, all the thermocouples are basically there. Chalmers University also presented about applying ParticleWorks to e-motor cooling. In this case, they had a little bit of a different system. It's not a forced lubrication with jets coming from the rotor or the stator, but actually is let's say a bath of oil type of lubrication. So the idea is to initialize or have some oil inside the e-motor, and then because of the splashing, due to the rotating element, this oil will cool down the most critical areas. So the objectives here were several. First, to understand how the losses, mechanical losses, churning losses due to oil could vary depending on the oil amount. But then again, the validation was done on the temperature prediction in the coils. So we see here different outputs of the visualization. So we increase the oil amount, we see an increase in mechanical losses, of course, at different RPM. So this is another standard output that was also validated. We don't have a lot of slides on that right now, but today public. But we can see an output, a common output that our customer look at. So the resistive effect of oil on the rotating elements and the power consumption because of that. And then, as mentioned, for the different configuration, actually, in this case, we see 3 thermocouple signals, and the experimental one are the dashed line. 3 thermocouples for different rotor currents, so different operating condition, electromagnetic condition, and the temperature in those 3 thermocouples are different, of course, and the trends are captured by the model. So another validation of the temperature prediction inside particle works, and this is the key because, of course, it's important to have reliable outputs from the simulation. Coming a little bit towards the second part and towards the end, we have now engine and piston cooling application. So one of the first application in the field was from Wärtsilä in 2018. So in this case, there was a naval piston with several thermocouples, 20 thermocouples, so a very, let's say, detailed distribution of temperatures. And basically, there is this closed gallery system in which oil can enter. And you can see here a different thermocouple location, the measured and simulation distributions. So again, very good agreement in trends. Not only that, not only a spatial distribution, but also a load distribution. You see that temperature, the simulated and the measured temperature correlate. There is a good, let's say, quite linear correlation here. When you have, let's say, different loads, higher load, of course, mean higher temperature in general. And you see there, while at 10%, we have this kind of distribution of temperature here, okay? So very, very promising results already at 2018. And right now we see a lot of application also to fine tune some aspects of the simulation. Andrea Bianco presented at last year at Particle Works Experience about, let's say, having a precise correlation, Nasser correlation to estimate the impinging jet heat transfer capability in this kind of system. So we see 2 types of jets going towards the piston. And the objective was, of course, to understand the flow distribution inside here, the temperature prediction of the thermal solver, and also the implementation of this Nasser correlation type of impinging jet estimation. So I will discuss in detail with one slide. So the idea is to build a specific correlation to estimate the transfer coefficient in this kind of system. So we see here the heat transfer coefficient due to oil at the piston side. So of course we see the jet impinging in this area with higher HTC. And here we see when we move farther away from the impinging area, let's say, Nusselt number and the heat transfer coefficient estimated in that area. Andrea Bianco was able to implement a correlation inside particle works that can really capture the experimental result and actually the correlation. So this is the theoretical correlation that we should have. The experimental results are actually in the squares, and we see the multi-zone HTC script developed by the engineer that is well able to capture all the zones of this impinging jet area. And the piston temperature was also validated against literature predictions. So we see here the average max and minimum temperature at the piston, and we see that is in line with the literature about this impinging jet type of correlation. By the way, the results were not only thermal related, temperature related, but also flow related, of course. And we can see here one undesired interaction between the jets and the moving piston. In a certain position of the piston, there was a very peculiar interaction on the piston side that was undesired by Andrea, for instance. So you can, as mentioned, have insights of your design by iteratively simulating with particle works. Let's discuss the two more papers and two more simulations in different fields, a little bit different fields, not only automotive, let's say internal combustion engine or transmission, but now automotive on a car body type of level. So Toyota presented at the SCE conference in Japan in 2017 this type of simulation. So we are now looking into a wading simulation. So you see here all the water simulated in particle works and the car entering the puddle. And the objectives here are different. For instance, you want to understand how much water can enter the car body. And also you want to estimate the loads, the forces due to water on the car body, especially on sensible plastic inserts like battery covers. So here are the validation, both in the splash patterns on the front. So you see here that splashing phenomena is well captured by particle works with a lower level in the center of the car. And on the right, we see the water intake when the car starts to enter the puddle. The water level actually in this area at the front of the cooling system, the radiator, we see that that level of water is well captured by calculation. By the way, for this kind of application, now we also offer a new feature. Particle Works has multi-resolution capabilities. So the idea is that we have regions of the simulation where the particles are redefined with a smaller particle size. So they are transformed, as you can see here, in smaller particles. So in the example of the wading, for instance, you could have at the radiator side a smaller resolution of particle. Of course, we don't want all the water amount to be discretized with the very small particle size necessary to study the flow in that area. So we can take advantage of multi-resolution to exactly do that. So redefine the particle size, like in this case, from 10 to 5 millimeter. And because of that, we are optimizing simulation times at the end. Because if you want to simulate everything at 5 millimeter, it takes 8 hours. But if I apply, let's say, the multi-resolution region, the slightly visible box here, only to the desired region, you can go to 3 hours simulation time. At the end, I want also to mention Lorenzo Iorio example of validation of particle works, in this case for plastic recycling machines. So it's very interesting type of application as well, because we will see that is not only fluid moving particle simulation, but also powder type of flow coupled with the water. So let me just show you. Basically, we have a system that has a flow of water mixed with plastic pellets, and the objective with this type of rotor is to separate the water amount to the plastic amount. Okay, you can see here a map of flow in particle works and what was observed experimentally, and you can see clearly in the area that there is accumulation in a specific region. So that was the first, so just from the first first simulation, the customer was quite happy to see this kind of flow, confirmation of the flow. Moreover, they also tested different, let's say, rotor, and they look into the power losses due to different rotor geometries. And also this one, the numbers are not public, but we receive very positive feedbacks in terms of also experimental validation in this regard. So again, we are looking into temperature prediction, but also losses due to interaction between rotating elements and fluid or powder. And also fast iteration of the design, because three, let's say, geometries were designed in less than 1 week and tested with simulation. And this, by the way, is the output at the top, is the amount of, let's say, plastic that is reaching the top. And you can see that we get faster separating time by improving the rotor geometry. So just to summarize, particle works is widely applied in different regions, both in automotive, but also mixing type of, or let's say, separator type of technology, mixers, external aerodynamics and fluid dynamics. So I just wanted to give you a little bit of an overview of the main most recent validation and features of the software. So here is a summary again. I would like really to ask you to, if you want to hear more or present more, since a lot of you also are customer, I would like you to invite to our incoming conference in Frankfurt. It's gonna be in Germany in September, and you can submit, if you are a Particle Works user, your abstract, and we can take a look, and then we will decide in April for the selected papers. So in general, you can present, but you can also come and visit us. And so just follow the QR code and you will see all the details. And now I think it's time for Q&A. So please, just as I went through a lot of application, maybe in a little bit of a fast way, of course, there might be some more detailed questions, so feel free to ask. There is the chat, and we have Dennis already asking one question. So first, simulation of oil-cooled motors and validation of the flow rate. There is an high impact of air coming from the rotor chamber. This impact, yeah, so basically I think what the first question is about is the influence of air on the flow distribution and the multi-phase flow. So we don't always suggest to include air explicitly coupled with the fluid. We have type of, so in the example that we saw in with NIDEC, actually in that case, air was not solved, but because of the, let's say, rotating speeds and the fluid dynamics of the system, already the method could provide good results, okay? So of course, including air could further improve, but it's not always necessary. So the air gaps, the second question was, the air gaps of modern e-motor are small. Is it possible to get valuable drag loss in meaningful time? Yes, I would say yes. The air gap can be studied, also taking advantage of the multi-resolution feature I mentioned. So there are companies looking into that. And for the multi-zone HTC definition, what other parameter beside Reynolds number you can use? Bogdan asks. So you can actually define turbulence regions depending on Reynolds, different thresholds. You can define, again, different correlation for different distances between the impinging area and the final position of the fluid. I would suggest Bogdan to have a look at our website, so ParticleWorks Europe, or send us an email about that. We can provide the full paper. So yeah, by the way, this is my email. If you want to understand more in detail some aspects of the simulation or the results, I can take a look at your question and understand what can be shared. Giulio asks, how do you model the energy losses in the bearings? So in that case, actually, there was an estimation of, let me just, so ParticleWorks cannot, sorry, you don't see my full screen, but so my, 1 second. Yeah, so let me, no, you should be able to see now the screen again. I hope so. So in regarding the question about mechanical losses, so this is again from Carraro presentation. So the workflow is as follows. We don't have a mechanical solver inside ParticleWorks, meaning we cannot estimate losses due to solid to solid interaction. But what we can do is to, so basically in that example, as you can see, we have bearings friction with losses estimated by ISO standard. But what we can do is to understand how the churning losses due to oil applied to the gears are distributed between the gears. Because the previous methodology inside Carraro workflow was to apply a distributed churning due to oil, but without, let's say, a differentiation between the different gears. But what you can see here is that actually different gear will have different amount of losses. So the lowest one has 50% of these losses. So when you apply the churning due to oil and the heating due to oil, you need to take into account this kind of distribution that is not linear. But again, the heat sources at the bearing side were applied to the thermal solver inside ParticleWorks, but were estimated by ISO standard. This is a meshless approach, yes, and we can simulate air in different ways. We can simulate with particles or with a finite volume solver. I discussed here the modules inside ParticleWorks, and there is a finite volume method and also lattice-Boltzmann solver inside ParticleWorks. We can also use another software that is called Recurdyne for seal deformation. So gasket or flexible elements can be can be, of course, modeled. So let me show you this example. In this case, it's a different type of application, but basically we have flow. We have flow in this flexible pouch. So this was analyzed with another solver, the flexible element, but inside here we have a flow of detergent, non-Newtonian fluid, that is injected, and then there is sloshing on the deformable object, okay, when moving the pouch around in the filling process of detergent. Burak asked if there are correlation about splash lubrication oil aeration for a high-speed gearbox application. We had a look at that, but it's private material, unfortunately. We don't have anything public, but yes, we can also do oil aeration type of analysis, so the bubble generation inside the oil phase. Roman asked, in a coupled fluid thermal simulation, how do you deal with the different characteristic time between the two physics? That's a great question. Actually, we don't sorry. Let me see if I can grab one slide. There are several strategies there in order to include or not the thermal simulation. So basically, we see here all the strategies to include the temperature prediction in particle works. And there are some coupled or uncoupled ways to study the fluid and the solid behavior. Basically, it's not super clear, but basically we can separate it, and it was done by Carraro, the fluid phase to the solid phase. So first we do the CFD, that is usually, of course, let's say it stabilizes the flow, stabilize in seconds. So we don't need to simulate minutes that are typical of temperature, let's say, evolution. Okay, so one strategy could be to run CFD first and apply then the boundary condition, as was done by Carraro, to a steady thermal only simulation performed in particle works. Okay. In other cases, you want to have a coupled simulation, but of course that will make the workflow, actually the hardware time, increase significantly. I hope it answered that. Thank you for all your questions. It's very interesting to see the interest and very on point question. So again, if you have more, feel free to ask now or reach out to us. And especially my suggestion is to go to our website, both for the conference, but actually also Particle Works Europe website, because in there you can find all the public material available on this validation, and you can also, let's say, register for incoming trial periods of the software. We have monthly events where we give you access to the software for 1 month, and we show you how to use the software, and we can work together to build your first particle work simulation. So again, my invite is to reach out to us if you're interested, and we can schedule possible next steps in your journey towards digitalizing the prototypes. Okay, if you don't have a question, again, thank you all of you for your interest and the participation of today's webinar. and I will for sure talk with you soon, and I hope I will talk with you soon. See you.